Hi everyone, and thank you for coming. Welcome to the non-rigid world again. uh, First of all, let me introduce the non-rigid state of motion problem. This problem consists in recovering the non-rigid shape and non-rigid motion together with a camera motion. This problem is ill-posed since many different 3D systems can have similar observations, and for this, additional priors are necessary. When a new frame is coming, the projection is different in the image plane because of the camera is moving and the shape is deforming. So far, most approaches in the state of the art are bad, and hence all frames are processed at once after the video capture. For the bad case, the applicability is offline, and normally the solutions can become very accurate depending on models and priors. In contrast, the sequential case, for the sequential case, the estimation is as the data arrives, frame by frame. The applicability is online and in real time, and the accuracy is normally less than much. So this problem represents an even more complex scenario because of the intrinsic strong ill-posedness of the problem. In this paper, we present a sequential solution to solve the non-rigid state of motion problem. Why is this important? To many everyday applications in many different domains. For example, from movie industry for augmented reality, experimental industry, sport industry, and in medical image, where a sequential estimation is mandatory to achieve an interaction between the 3D models and the medical team. In this paper, we propose a new shape-based interpretation built from a red shape to encode the non-rigid deformations. This basis is computed by spectral analysis at low computational cost, a key factor for real-time applications, and no training data nor a deformation model is required to compute the basis. To this end, our approach consists in two stages. For the stage 1, we use a few unitary frames to estimate a shape address by using a rigid factorization algorithm. After that, we obtain a distance matrix using, for example, an Euclidean or Manhattan metric or another one. And finally, we apply a spectral analysis of this shape to obtain a reduced model shapes by solving a simple eigenvalue problem. In the second stage, our system continues operation in a sequential manner, performing a bundle adjustment over a sliding temporal window to estimate the model parameters, camera, and shape deformation. While most techniques use a few shape bases to encode the deformation, in this paper we employ a reduced shape basis that later we have to interpret. In this case, these shape bases correspond to the eigenvectors of a distance matrix, and the corresponding time coefficients are to be interpreted on the fly to code the shape deformation. Of course, in a 3D space, we have 3 interpretations per eigenvector, so we can obtain 3 model shapes per eigenvector. This is our energy function by minimizing an image reprojection error for all visible points over all frames in the temporal window, and the temporal smoothness terms for shape and motion. Regarding experiments, our method outperforms current state-of-the-art sequential and batch methods in terms of accuracy and efficiency to obtain the shape basis. And here we saw more experiments for real videos, for example, for a paper bending, phase, or laparoscopic sequence. To conclude, our approach in this paper, a spectral decomposition of the data produces a reduced shape basis with physical interpretation. Our approach is able to make the most of the available information and is suitable to model a wide variety of deformation and objects. For see videos or more information, come and see our poster. Thank you so much.